Any questions? So we're going to continue doing some calculations. Let's look at number 18 next. Number 18 is another equilibrium style calculation. So let me just, at the beginning, just go through and give you the general format. For equilibrium calculations, the type of stoichiometry setup that we do is always the same. This is going to hold true for chapters 15, 16, 17, and 18. The basic setup is the same. The basic setup, let's say we're given a case C, and we have the reaction AA plus BB plus dot dot dot. This goes to GG plus HH plus dot dot dot. We're always going to set this up in the ICE table, or the ICE table here, initial change equilibrium. And so when we look at all the entries here, the first entry would be the initial concentration of A, the initial concentration of B, initial concentration of G, H, etc. Sometimes these are zero, sometimes we're given the concentrations. So some of the observations that we saw earlier, we were given the reactants, we had zero products, and then they tried having products but zero reactants, and then they tried having both products and reactants present initially. And so the initial conditions can vary depending on how you want to set up the experiment. Okay, but there's going to be a change that takes place, and last time the change, the change isn't necessarily 100% or 0%. Like 0% would be no reactions, no change. 100% would be complete reaction. In Chem 1A, that's the type of scenario you had. You either had no reaction or you had complete reaction. In Chem 1B, we're going to have this partial reaction due to the reverse reaction taking place. So we don't know how big the change is going to be. It might be complete or it might be zero. And since we don't know, we just call it X. But we got to make sure that we, obey the conservation of mass. That is, atoms are neither created nor destroyed. And so they have to react in these ratios, the little a, the little b ratio. So we're going to lose maybe minus AX, minus BX. And then over here we'll form plus GX plus HX. Sometimes it's easy. If we're given product and zero reactant, the only way this reaction can go is forward, right? But sometimes we're given product and zero reactant. And so if we have zero reactant here, how can we lose it? If you have nothing, how can you lose? Like, if somebody asked to borrow $10 and you had $0 in your wallet, could you give them $10? No, and so negative values are positive. So sometimes it goes in the reverse direction, like plus AX, plus BX, because we have nothing here, but we have product here, and since these reactions are reversible, we can get a minus GX and a minus HX here. So the direction, it can go in either direction depending on what the initial conditions are. And so at equilibrium, we have this scenario where the equilibrium is going to be the initial minus or plus depending on the direction. So I'll just say minus plus AX. And this is what we call the equilibrium concentration of A. And then for B, it would just be B initial minus or plus BX. And this is the equilibrium concentration of B. And then we have G plus or minus GX equals GEQ. And we have H initial plus or minus HX, little h, which is equal to HEQ, concentration of H. And so this is our basic stoichiometry setup. We set up every problem the same. If it's a KC problem, we set it up like this. If it's a KP problem, a KP problem, rather than working with concentrations, we work with pressures. And so instead of having concentrations here, we just replace all these concentrations with P for pressure. And it's the same thing. So, the concentrations are always going to be in, we would put in the molar value of the concentration. The pressure is always going to be in atmospheres. So we'd use the atmosphere value of pressure. That's by convention. And so we just try to fill out the table the best we can, and that's what we did in problem number 17. We filled in the remainder of this table. Sometimes we're given like two unknowns, for example, B initial and X is unknown. If we're given two unknowns, we need more equations, right? Multiple equations, multiple unknowns. This is the only way we could solve it. And so for something like this, is there another equation that we can generate? And the answer is yes. We can generate the Kc equation. The Kc equation is just going to be G raised to little g, H raised to little h, dot, 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 over A to little a, B to little b, dot, dot, dot. And so we got this Kc. This Kc equation, we plug in the equilibrium values here. But we see that the equilibrium values are also equal to the initial plus or minus the change. And so what we can do is we can come up with another equation here. For example, G at equilibrium is actually equivalent to G initial plus or minus Gx. This is going to be raised to little g power here, the whole thing. And then H at equilibrium is H initial plus or minus Hx, raised, the whole thing raised to H, little h power. And then we got the same for A, minus or plus AX, little a, and then B. Etc. However many terms we have. And so this, this is pretty much it. And we're going to be given some data, some numbers in here, and all we have to do is do some algebra to figure out what's missing to complete the table. And so 15, 16, and 17, and 18, we do this. Is this it? We do 4 chapters of the same thing? No. It starts off easy, or relatively easy, because we're only given one reaction. But pretty soon we're going to be given 2 reactions that occur simultaneously. What do we do with that? How do the 2 reactions interact with each other? 3 reactions, 4 reactions. And so as things get complicated by having or introducing other reactions that occur, it can get quite complicated. And so we need to get just the basics down first and then learn all the tricks in solving this initially, and then add complexity to it later. And so in chapter 15, we're just dealing with one equilibrium reaction, one ICE table. Whether it's a Kc like this, or Kp, what would the Kp table would look like? The same thing with pressures, right? The Kp over here, we put pressures instead. Or we would have something a little bit more mixed up, and that would be a Keq. What would the Keq table potentially look like? It would be all concentrations, all pressures. It could be a mix. And so we'd have concentrations and pressures mixed up. But that's only for Keq. You'd never do it for anything else. So we have to be careful. So let's try some more examples here. Let's do number 18. Kc is probably the most common. Concentrations are common. So here, mixture of 1.00 grams of hydrogen, 1.06 grams of H2S in a 0.500 liter flask. So we can calculate the concentrations, but it depends. This is at 1670 Kelvin, and it's brought to equilibrium. The equilibrium amount of S2 found is 8.00 times 10 minus 6 moles. Determine the value of Kp at 1670 Kelvin. And so here, you know what? We need to set up a Kp table for this. And so let's go ahead and set up a Kp table. for this particular reaction, and we got 2 hydrogens, gas, plus S2 gas. We're going to be in equilibrium with 2 H2S gas. Now, basically, I'm just going to plug in the values here, or should I write out? Maybe I'll just write it out so that you can see, and then we'll plug in the values. Well, to fill out the tables, I need the partial pressure of hydrogen initial, the partial pressure of S2 initial, the partial pressure of H2S initial. And then there's going to be a change. Do we know the direction of the change? No. The change could either be forward reaction or reverse reaction. So we'll just do forward. Minus, okay, in this case, what is A? Little a. 2. And so this is going to be minus 2x. And the units for this are going to be ATM minus x ATM plus 2x ATM. It has to follow the mole ratio. It's a 2 to 1 to 2 mole ratio. Otherwise, we're going to lose atoms or create, we're going to create or destroy atoms, which we can't do. Atoms are conserved. This is if it goes forward. But what if it goes backwards? Then it's going to be plus, minus. Well, how do we know? How do we know if it goes forward or backwards? How do we know?
We can start with the initial concentration.
Yeah, and so let me talk about that right now. I should have talked about it earlier, but how do we know which way it goes? There are 2 ways to determine. The simplest way is 1. The reaction goes towards the 0 values. And so the reaction in direction of 0. So let's say if we have 0 product, the reaction can only go forward, because from 0 we can only build up. But if we have 0 product, can the reaction go in the reverse? Yeah, I mean, how can we lose something we don't have? In other words, if somebody asks you to weigh out negative 2 grams of H2S, is it possible? I mean, how could you weigh out negative 2? It's impossible. You could take 2 grams from 20. That's easy. You're left over with 18 grams, right? But you can't take 2 grams from 0 because there are no atoms there. And so the reaction is going to proceed in the direction of the zeros. Or 2, we do this. We determine Q. There's something called QC and QP. QC is, G, G, H, H. It looks exactly like K. A, B, B, dot, 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 dot. It looks exactly like K. The only difference is, rather than having equilibrium, we have initial values there. And it's easy to determine here because if QC is, let's say QC is greater than KC. If QC is greater than KC, that means we have too much product. So too much product or too little reactant. So too much product. It's top heavy. And so if we've got too much product, the reaction has to go in the reverse. So the reaction proceeds in reverse. If QC is less than KC, then we don't have enough, We need more product. And so too little product or too much reactant. And so the reaction's got to go forward. If QC is equal to KC, then no change. Why no change?
It's already at equilibrium.
Yeah, because it's at equilibrium. Would we use a QC here? No, we wouldn't use a QC here because they're asking for KP. And so we have the equivalent. we have QP. And so QP, well, let's just figure out what QP is for this. QP for this would be the partial pressure of H2S squared divided by the partial pressure of H2 and squared divided by the partial pressure of S2 to the third. And these are going to be the initial values. And so at equilibrium, we'll just have, the initial minus the change. That'll be the equilibrium value. So this will be 2 plus 2x. And I'll just write it in here. Plus x, minus 2x. Minus or plus 2x. Etc. And we fill out the table, right? But what we want to do is we want to put the numbers in here and then figure out what the missing entries are. And so let's go ahead and place the numbers in here next. And so I can calculate the initial pressures here for hydrogen. I don't have to put some generic one in there. The way I can calculate the initial pressures is use the ideal gas law. We have 1 gram of hydrogen, so how many moles is that? It's 1.00 grams. So go ahead and do that here. Close. Yeah, I want a little bit more sig figs, so I would do 1 divided by 2.016, 0.496. 0.4960 moles of hydrogen. And if I have that many moles, then the pressure is equal to nRT. And so moles times R, 0.08206, times T, 1670 Kelvin, divided by V, 0.5. 135.95 atmospheres. 135, but how many sig figs are we allowed? Just 3. And so this is 0.95, but I'm going to carry an extra 1. I don't round it. Even though I'm dropping a 5, I don't round this up, because this is already an extra digit. I'm only allowed 1 rounding step, and that's at the very end, so I don't want to do any intermediate rounding here. And so this is 135.9 ATM. Let's calculate the pressure of S2. What's the initial pressure of S2? I don't see any S2 there. I do see the equilibrium amount of S2, but what was the initial amount of S2? The initial amount of S2 is actually 0. We can assume that they didn't put any S2 in here. It makes sense since S2 is not very stable. So they have a 0 atmospheres of S2, but they did put some H2S in here. Let's see how much H2S they put in here. It's 1.06 grams of H2S. And so what's the molar mass? Let's do it. So 1.06 grams of H2S divided by the molar mass of H2S would be 34.909. 34.09. That's a mole.
I got 2. So not 9. I got 34.082.
34.082?
Yeah.
What did you use for hydrogen?
I used 1.027.
Okay, 794. All
So
right.
you went to 8 then?
No, I use 1.01.
Oh, okay.
The reason I rounded it is I normally, when I use hydrogen, I usually go 101 because most of these I just use to do decimals places.
Okay.
Only when I use hydrogen alone, I go 108. That's only kind of like I use it. So for example, H2 I calculate 1016. I wouldn't calculate a 102 because it doesn't give me 4 sig figs. I want 4 sig figs in all my molar masses. And so this is why I did it. But you don't have to, you could use more accurate, that's fine. So we could use yours. But just be consistent with mine to get the same number as always. And so I'll do 1.06 divided by 34.09 moles, 0.03109 times R, 0.0206 times T, 1670 divided by V, 0.5. And so I get 8.522. Actually, I'm only allowed 3 sig figs, so 8.52 sub 2 atmospheres. I carry 1 extra digit to avoid rounding off error, and just do that consistently. All right, here we can calculate the direction, or we can just look at it and see what the direction is. Can you look at this and tell me what the direction is going to be? Can the reaction proceed in the forward direction? If the reaction proceeds in the forward, we got to lose reactant and gain product. How can we lose S2 when we don't have anything to lose? Right? So we cannot go forward. If you were to calculate QP, then the pressure of S2 is 0, which means QP is infinite, which means it's way too big. Right? The reaction's got to proceed in the reverse direction. And so the change here is going to be plus 2x atmospheres, plus x atmospheres, and minus 2x atmospheres. Here will be the change. And so at equilibrium, I'm going to get 135.9 plus 2x quantity ATM, x ATM, 8.52, so 2 minus 2x ATM. So here's my table that's set up. But let's see if they give me enough information, because right now I need to solve for x, but I don't know what x is. And so looking at the problem, they give us some additional information. The equilibrium amount of S2 found is 8.00 times 10 to the minus 6 moles. And so they tell me at equilibrium I'm going to have this many moles of S2. How many atmospheres is that? And so let's go ahead and calculate the atmospheres. For that, I have 8.08, well, just 8 times 10 to the minus 6. Times R, 0.08206 times T, 1670 divided by B, which is 0.5. And so it turns out at equilibrium here, I have 0.0021, well, 2192 atmosphere. And so from that, I can figure out what my x value is. If I know what my x value is, then I can determine what the other entries on the chart. And so this one is going to be 135.9 plus 2x. And so plus 0. It's going to be 0.002192, which gives me 135.90292. Oh, you're right. I didn't double it. I need to double it. What does it come out to?
0438.
438?
Yeah.
0. 4? 4. Okay, so this comes out 904,384. All these are insignificant here. Atmospheres. And then over here, I'm going to get 8.522 minus 2x. So it's going to be minus 0.004384. And so let's carry this out. This will be 10 minus 4, 6. 9 is 1. 9, 6, 11, 4, 7, 1, 5, 8. So those are the equilibrium pressures of this. When you look at this equilibrium pressure, did it change much? No. What would you say about that change? The change didn't even register because once we round this, it looks like it's the same number. But it did change. It was a negligible change, that's all. This is a little bit more significant of a change because at least this change registered on this. But when we round it, it looks like it's the same because when we round these, it's 852. We end up at 852. I mean, we're going to round that up. So it looks like if we start at 852, we end up at 852. We start at 136, we end up 136. So it looks like no change happened, but actually there was a change. The change was just so small, it didn't really impact the number. All right, so what are we trying to solve for? KP. So let's go ahead and do that. KP is going to equal the partial pressure of H2S at equilibrium squared. It's going to be 8.517. I just carry one extra digit. That should minimize round off error. And then 135.9 squared and 0.002192. This comes out to
1.79.
1.79? Okay, give me one more digit. 0, 1.790. Is that what everybody got? You got a different number?
1.793.
You got 1.793? It depends on how many digits you carry in your calculator. 1.793? Most people got that? Yeah, okay. We'll go with that one. 1.793. You could either leave your final answer like this, or you could round it. If we were to round this, it would round to 1.79. And that would be the only rounding step we're allowed. You know, the final rounding step. Okay. Again, don't do intermediate rounding step. And so they're asking for KP here.
So that's the pressure at equilibrium.
No, this is the ratio of the pressures at equilibrium.
All right.
KP. Now this is a constant. And so what do we do with this number? Well, obviously it'd be nice to get more, so you'd like to do like 3 trials or something and get the average. But once you have an accepted value of Kp, what can you do with that? Well, you can do any reaction, and any setup we do, you know, actually when I say any reaction with, you know, different pressures here. The reaction has to be the same. The overall reaction is the same. That is, hydrogen and S2 yields H2S. But we could start off with any conditions initially and then figure out what the final conditions will be, where this reaction is going to end up. Because where the reaction ends up is going to be here. The ratio at equilibrium has to be this. And so we might not have that ratio initially, but by the end, it's got to be that ratio. And that's how we'll figure it out. So let's take a look at another problem here. So this problem, to sum it up, this problem was just using experimental data to determine the value of K. And we want to know the value of K because K is what we're going to use to make predictions about the stoichiometry. And so number 33, we take a look at this reaction. Hydrogen plus iodine gas yields 2HI gas. And they give us a Kc value. The Kc value is 50.2. Hopefully this Kc value is based on multiple experiments, so it's a reliable Kc value. When we got this Kc value here, then what can we do with that? Well, we can make stoichiometric predictions because we know what the final ratio is going to be. If we know what the final ratio is, then we can be given any initial ratio and then figure out what the final ratio is. And therefore, we can figure out what the change is going to be, i.e. the stoichiometry. And so, taking a look at number 33, we look at the reaction hydrogen gas plus iodine gas yields 2HI gas. And so they say, well, this is a Kc. If it's a Kc, we want to deal with molarities. So they give us the moles. And so we have to make a distinction between amounts and concentrations. Amounts are typically like moles, grams, etc. Concentrations would be molarity, right? And when we're dealing with this, is moles and molarity the same thing? No. And so when they're asking for the the final mole ratio here, we need, or are they? No, it's not the mole ratio. It's the molarity ratio. And so a lot of people, what they do is they don't bother converting from moles to molarity. They just go ahead and use moles because typically in stoichiometry you use moles, not molarity. But we need to shift our thinking. And to do this, I'm going to do everything in molarity. And so the first thing we're going to do is convert from amount to molarity here, 0.15 moles divided by 3.25 liters. And so what does that come out to? And so 0.15 divided by 3.25 gives me a molarity of 0.0461. So 0.0461 sub 5 molar. Carry one extra digit. So this is my initial concentration of hydrogen. And the same thing with iodine. Well, iodine turns out to be the same, 0.15 over 3.25 liter. So it's 0.04615 molar. How about my initial concentration of HI? Do I see that in here? No. And so if it's not given, then typically it's 0. I don't have any product. And so I'm just mixing reactant here and then seeing what forms. And so how much reaction occurs? Well, in Chem 1A, you just assume 100% reaction. So at the end of this, you'd have 0 molar, and double that, right? At the end of this. So this is not a Chem 1A. This is a Chem 1B, one of these partial reactions, these equilibrium type stoichiometries. And so we got to figure out the change. Can you just look at this and tell me what the direction of change has got to be? Yeah, it's got to go left to right. I mean, we can't go negative, in other words. So it's going to be minus X molar because coefficient is 1. This is going to be minus X molar. And this is going to be plus 2X molar. So this will change. And so at equilibrium, I'm going to have 0.0461 sub 5 minus X molar. 0.04615 minus X molar and 2X molar.
If this is gas, don't you look for the pressure?
Gas, you have the option. You could either go molarity or pressure. Yeah, you can go either way because they're both related. As the molarity increases, the pressure increases. In fact, they're directly proportional. When we look at the ideal gas law, P is equal to nRT over V. N over V is just the molarity. And so the pressure is equal to molarity times RT. And so the pressure and molarity are directly proportional to each other. And this is a constant. RT is a constant. And so, we could use either for gases. Now we got to figure out what X is. Do they tell us what X is here? Do they give us any equilibrium amounts? No, they don't tell us what x is, so how are we going to figure out what x is? Yeah, we need another equation. And fortunately, they tell us what Kc is. They give us a value for Kc, which is 50.2. And Kc's depend on temperature, so this is why temperatures are typically written with the Kc's. If temperature is not given, then normally we assume room temperature. Room temperature is what? In Kelvin. Do you know what room temperature is? Not 273. 273 would be an awfully cold room.
373.
Not 373, it'd be an awfully hot room.
313.
It's just going to be a warm room. Maybe a little too warm. I don't know why they picked it. That's 298 Kelvin, 25 degrees C. That's your standard room temperature. Maybe uncomfortably warm. But anyway, Kc, we can figure out the equation for Kc. Kc is going to be the equilibrium concentration of Hi squared divided by the equilibrium concentration of H2 and the equilibrium concentration of I2. Well, we don't have the equilibrium concentrations either, so it looks like we're stuck. But we're not necessarily stuck because we do have the initial concentration. So the equilibrium concentration of Hi is just 2x. Let's plug it in here. It's going to be 2x quantity squared divided by 0.0461, so 5 minus x times 0.04615 minus x. Now can we solve for x? Yeah, now we have one equation, one unknown. We can solve for x. So let's go ahead and solve for x. When we solve for x, we get 50.2 is equal to 4x squared. And then let's multiply this out. Minus x times minus x is x squared. And then minus this minus that will give me minus 0.0923. 0.09230x, and then square this 0.04615 squared, which is what? 0.00212. 9.8. We're only allowed 3, so let's just carry the 9, drop the 8. All right, then continuing with this, let's multiply both sides. So this is 50.2x squared minus, what's 50.2 times 0.0923? What is it? 4.63. Give me one more digit. 3. X. What's 50.2 times 0.02129? 0.1098. This is equal to 4x squared. And then let's subtract 4x squared from both sides. So we get 46.2x squared minus 4.633x plus 0.10978 is equal to 0. Then we use the quadratic formula to solve for x. Using quadratic, x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. We could do that. Or we could use our calculator, SAT approved calculator that has a quadratic solver. Do you have that? Or just
Scrap, maybe.
did anybody buy it? The calculator? No? Well, if you're sitting at home doing this, then obviously you can use the web-based quadratic solver. It's fine. So 46.2. I don't, on the test, unfortunately, you're either going to have to use the quadratic or because the programmable calculators aren't allowed on the test. Minus 4.633.
I think it's 0.062 and 0.0378, but I'm not sure.
Okay, that sounds right. How did you solve that?
Oh, I programmed it in my calculator.
Oh, okay. Well, here it is. So we get this. We get x is equal to 0.06186. Actually, how many sig figs are we allowed? We're allowed 3, so let's go ahead and use them. 0.06186 or 0.03841. Now, only one of these will make any sense. So, for example, let's just use 0.0618. And so if we have 0.046
Negative.
minus 0.06, 0.04 minus 0.06 gives me negative molarity. Is that even is it possible to make a negative molarity? I guess if you can weigh negative grams, you can get negative molarity, right? But it's impossible. And so only one of these will make sense. And so it's got to be 0.03841. I highly recommend that you get a calculator that does quadratics. Otherwise, solving the quadratic formula just takes time away from other problems. And I don't care if you know how to solve it using quadratic formula or not. So here we're going to 0.04615 minus 0.03841. So that works out to a positive molarity at equilibrium. So what does it come out to? It comes out to 411.7. 0.00774 molar. Even though I was allowed 3 sig figs, but I end up with, no, I only ended up with 2 sig figs. Why?
Rounding error.
Not rounding error, because the rules for addition and subtraction are different. Right? It depends on decimal places. And so really I should have said I'm allowed 4 decimal places, and I end up with 4 decimal places. And so over here I'm going to have, actually this should be the same. So this is going to be 0.00774 molar. And then 2x is, I erased my x, but it's here. 2x is double that, so 0.07682 molar. All right, so after this reaction has run its course, did we consume all the reactants? No. And so we're going to have leftover reactant that's just not going to react. This is it. This is the end of reaction. It doesn't go all the way. if you want to know the percent, what percent reaction did we have, we could figure it out. You just take the change and divide it by the original. The percent reaction is kind of high. So let's see what the percent reaction comes out to. And so I'll just take the change, which is 0.03841, divided by the original, 0.04615. And I had about 83% reaction here. 83, not 100%, 83% reaction. But, I want to check my answer. How do you usually check your answer? Normally when you check your answer, you look it up in the solutions guide. But what if there's no solutions guide available? Is there a way to check this answer? Yeah, there is a way. We want to double check our answer, and we don't need the solutions guide for this. What we'll do is the ratio, this equilibrium ratio must equal the Kc that we just have. And so let's calculate the K. It's going to be 0.07682 squared divided by 0.00774 times 0.00774. So just square it. And so what does this number come out to?
I got 0.397.
0.397?
Mhm.
0.397. What is K supposed to equal in this problem? Which one did we get? 50.2. And so I'm getting 0.397, and the K is supposed to equal 50.2. Which means, that's close enough, right? This is just due to experimental error, right? Close enough. Or maybe that's what we call round-off error. I like experimental error because we could use experimental error to explain everything. Experimental error. What do you think? Is that close enough to 50.2? It's supposed to, the final ratio is supposed to be 50.2. I'm getting 0.397. There's something seriously wrong, right? A mistake was made. And so what we need to do is we need to go back and find out where that mistake is, because this is just way off. And so we do double check. The first thing is maybe we double check this calculation just to make sure.
Oh wait, actually I redid it. And I got a different answer.
All right, let's try. Let's try.
98.5.
Yeah, if you get a different answer, then you should do it again. 98.5?
Yeah, that's what I got.
Still
I thought it
off,
was.
All right, 0.07682 divided by 0.00774.
Forgot to square it.
And then square that. Actually, I can't get the square on my calculator.
Oh, you can do it.
Is your screen locked? You have to
Yeah, I must have screen lock here. Let's see. There it is. Okay, let me get my square. What did you get? 98.4?
Yeah.
I got 98.5.
98.5.
Yeah.
You got 94.
.985? Is that it? .985?
Either.
Well, it's a little bit better.
No,
98.
98.5.
Oh,
No, I don't know if it's any better. It's still way off, right? That's
But it's closer though.
that's not good.
Closer
Yeah.
though. It's closer. On the other side extreme.
Right. So let's try to figure out where the mistake was made.
Maybe the starting molarity was off.
Was it the starting molarity?
No.
So we double check that.
Wasn't
And then double check. I'd erase all the equations, but we can go back through and double check the equations. Did I get it in the correct quadratic form? Or did I make a mistake in the quadratic form? Maybe I screwed up. Did I screw up the sign?
Oh, I
The
see.
sign.
Yeah, right here.
Okay.
Yeah, when you set 50.2 equal to 4x squared divided by x squared minus 0.0923 x plus 0, I think you made a mistake.
Yeah.
Okay. So well, we'll start from here. 50.2 equals 4x squared divided by x squared minus
0.0923 0x plus 0.002129.
The size wrong.
Okay, which sign is
The x was supposed to be negative.
oh, but I made it positive.
Mm-hmm.
Okay. Okay, so
Negative times negative?
Yeah.
It's positive.
then I went to 50.2x squared minus 50.2 times 0.0923.
But it's times negative.
Yeah. So that's negative 4.633x. And then 50.2 times 0.002129 is plus 0.1068 is equal to 4x squared. And then subtract 4x squared from both sides, we get 46.2x squared minus 4.633x plus 0.1068 is equal to 0.
Because we have written 0.1098, not 68.
0.0198, not what?
.1098, not 6.
Oh, okay. What is it supposed to be? 6.8?
Yeah.
No,
All right.
98. Oh wait, that's 56.8.
It's supposed to be 6.8. So I guess I just misheard it then or something. Well, let's try that again with the quadratic solver with these new ones, and hopefully this comes out better. And so 46.2 is the same, negative 4.633 is the same, but 0.0198 should have been 0.0168, which gives us a different value for x. And so let's redo.
But I think it'd still be close to
The x is going to equal 0.06436 or 0.03591. The 0.06 can't be because, right, 0.04 minus 0.06 is going to go negative, right? And so let's go ahead and use the 0.03591. So 0.04615 minus 0.03591. You know, a lot of people will say, what's the big deal? 359 versus 360 whatever, right? But, you know, this is why I always say do not round. When you do these little rounding steps can really impact your final answer. And even though it doesn't seem all that different, when you start to round and you know, some people are so lazy, they don't even want to write this. They round this to 0.04 and go 1 sig fig because it's just a lot easier. I only have to punch in 1 digit in my calculator, right? But, you know, their answers are so far off that either they correct that or they just don't pass. Because they never get the right answer. 11, 2, 5, 0, 1. And so this is going to be the same, right? And then 2 times that is going to be 0.0718, 182. Is that right?
Yes.
All right, so now let's repeat the K calculation for a double check.
Wait, so we're gonna roll.
Repeating the K calculation, K is going to equal the product squared. So this is 0.07182 squared divided by 0.01024. The bottom is going to be squared too because it's the same.
I got 49.219.
49.19? 49.219.
I know what I got 49.49.
I got 19.
Yeah, 49.19159.
Okay. What is it supposed to be?
50.2. But then if we took more numbers, we'd probably get closer to that.
50.2 it's supposed to be.
We're closer.
So do you think is that close enough?
Yes, because you're round. It all depends on how you round.
Well, you know, we're minimizing the round off error by carrying an extra digit. If I started rounding, maybe it's close enough, but you know, since I was carrying extra digits, this isn't close enough. And I would expect it to be a little closer than this, you know, because I would expect at least this should come close to rounding to this. I mean, if I round this as 49, that's 50. Maybe that's close enough, but
Wouldn't that be a
that's only 2 sig fig. No. Calculation error. This is a calculation error, so I got to figure out where did I make my mistake in my calculation again.
Wait, so we're
3, 8, 5.
And so I need to do, well, you know, the reason why is this morning I did this calculation and it came out to 50.19. 50.19, well, you know, 50.19 versus 50.2 rounds to the same, to 3 sig figs, right? And so this is kind of off. And so there's a mistake here. And so we need to find out the mistake. This is good because this, you know, we don't need the solution manual to tell us we got the wrong answer. We can figure it out. We got the wrong answer. And so we should figure out where that mistake is. Right? And so we go back through and we take a look for the mistake. But I'm not sure if I have enough time to do this. We're at 12:35, and I do want to cover a couple of other problems. But let me just check some of these calculations. So we're going to just double check the calculation. So here, 0.15. You know, the initials, even if I got those wrong, you know, if I put the wrong initials here, I mean, I'm going to get the wrong answer, but it should double check to the correct answer. And so this could fool you because, you know, you'll get the final ratio correctly, but if you input the wrong initials, right? And so even though the initials I might have calculated wrong, that shouldn't impact things. Right? And so here, the initials are right? Okay. And then I go over here. And double check the other calculations, unfortunately. And so KC is 50.2. And this is going to equal 4x squared. And then did I multiply these out right? So 0.04615 squared. 0.0021. Did I write 0.00212.9?
Yes.
And then x squared. And then 0.04615 times 2.
Yeah, that was good also.
That's right also. 0.0923.
Yeah.
Zero. All right, then we multiplied it through 50.2 x squared. I think I double checked all these already, huh? Times 50.2 gives me minus 4.633 x.
I got 4.615.
You got 4.615? And then one final one, 50.2 times 0.00. You might have carried extra digits. 129. 1.068.
Yes.
That's what we had. This is equal to 0. Well, I guess that's it. We double checked everything.
Is it equal 4x squared?
Yeah.
Yeah, this is equal to 4x squared. And then subtract 4x squared from both sides, 46.2x squared minus 4.633x plus 1.06.
Isn't it 0.1068?
Yes.
Not 1 point.
Oh, yeah, 0.1068. Which is what we had before, correct?
Yeah.
Yeah, shoot. And then I plug it into the quadratic equation solver and 46.2, 4.633, 0.1068, and this is the root we get. And so we double checked everything, so I'm not sure why this morning maybe this morning I made a mistake, and so maybe this is it. Maybe it is 49, what did we get? 49.18. Let me just double check that calculation here. And so this is going to be 0.07182 square.
For the x,
Mhm.
I got 0.035959, not.
Would it be the accuracy of like the quadratic formula online versus if you actually did it out?
It could be. You know, this morning they didn't. This morning somebody had their Casio FX115ES, so that's what they use. But you're getting a different number for x.
Yeah, I got.
I don't know which.
0.035959, not 5913. So it's.
Oh yeah, that would make the difference there.
Wait, what did you say?
Let me try a different quadratic solver. So using this quadratic solver, 46.2. I don't know what algorithm they use because these are just
Negative 4.633
4.633.
and 0.1068.
0.1068. I thought they all use the same. 0.0359. You got 0.03599?
5959.
5959? Okay. 5959 would make a difference. But this is getting the same as before, so these probably use the same algorithm. Well, you know, I have my calculator.
Try mine.
And this is bugging me. So, I'm gonna just get my Castillo. I'll be right back.
I got 50.2.
50.2?
Like, I don't know where it was, like, something had to become a 9. Oh yeah, I forgot where it was. Oh yeah, it was the x equals to 0.03591. It's supposed to be 0.3599.
99, and how did you solve that?
I'm trying to, I don't know how to do it. Oh, I think,
Did you use a quadratic equation?
shoot, sorry,
All right.
I went somewhere in my.
Okay. You know, I'm just curious. I need to know because
Oh, no, okay, now I remember.
I need to know because somebody punched it in the Castillo this morning, the exact same numbers, and now I'm punching it in the quadratic solver on the web, and I'm getting maybe different numbers. I need to find out.
I figured it out.
Okay,
So
what-
for our C, it's supposed to be 0.1069, not 8.
1069. Did you round it?
Yeah, it was like, because like the whole digit was like 8 or something.
8. You don't round it. You just drop it. I know dropping digits is going to. You know, the more digits we carry, the closer our calculation should be. And so if it's coming off, you know, but the thing was, it's coming off too much. So for example, if it was like 50.1, it's probably because I didn't carry enough digits here. And it's probably just due to round off error. You know, I'm dropping digits. And if I carried all the digits in the calculator, then it should come out, you know, 50.20, whatever. But in this case, 49 is a bit off. It's too far off. 49.1 when it's supposed to be 50.2 is too far off. And so I just want to see something just really quick. I'll be right back.
You got the letters?
So I went to 0.03.
So this is the calculator that I use. You could get any comparable calculator, but this is the Casio FX115ES. And the student in the morning class just told me he went to Target, they're out of stock on these, and CVS, they didn't have any there. And so then I just checked online, and you know, Walmart on Hawthorne has some in stock, but Walmart over here and Normandy doesn't have any. And then another student told me she got hers for $9 on Amazon. So Amazon. So anyway, I just use this. It has an equation solver. I'll just plug in quadratic equation 3, and then let's see. You know, because I want to come to a conclusion with this, and I just need to know, was this morning off? And this is right? Or was the morning right, and this is off? And so let me just see, because I'm not sure how they programmed this to calculate the quadratic.
Could you watch the clip of the morning one? And
No, because the morning lab, I just asked, you know, who solved it, and they just punched it in their calculator, and they just gave me the x value. And so I know what the x value came out from the morning class. And it comes out the same, 0.03591. And so what this means is this. I don't know. I don't know why I got it different. Maybe somebody rounded it off in the morning, and that's why it came out to 50.2. But if it's coming out to this, when we punch this out, let me back out of this. Well, the reason I want to go through this is because what do you do on a test? You know, is that close enough, or is that too far off in your calculation? And so, what did this come out to when we calculated these numbers again? 49.1. It's supposed to be 50.2. That's too far off. And so what we have to do is we go back through and see, is there a calculation error? Or could this be a round-off error? And so if we go back through and we look at all of this, then maybe it's a round-off error because we double-checked our calculations. And so the only way to actually determine this, and this is too much work, is to carry more digits. If we carry more digits, and then we get closer to 50.2, then that should be round-off error.
So this was a test, and you know I got 49.1. Did you mark that wrong?
Well,
If everybody got 49.
If everybody got 49.1.
If everyone got different answers.
no.
It was in the ballpark.
Okay. To answer that question is, it depends. You know, if this were a test and you got 49.1 and you carried out all the digits to what you're allowed and still the round-off error resulted in being off, then no, I wouldn't mark you down. But if you got something, the K was off like this because you decided, well, I don't want to carry that many digits. I'm just going to round this to 0.036 to make my life easier. Or I'm going to just round it to 0.04, you know? So if you do this intermediate round off and you aren't carrying all the sig figs that you're allowed, then for sure you're going to be off, right? And so it depends if this. And so this is still bothering me because it should be a little closer. But if it is round off and we did carry all the digits, then we should be all right. You know, this is as good as we're going to get. I just thought we were going to get better. And so I was just thrown off because this morning somebody came up with a number. I didn't double check it, and now I got to double check it. Okay. And so I got to figure out what exactly happened here.
For the test, are you allowed to carry more sig figs?
You can carry more digits, but just at the very end, you round it. That's what you do.
When I got the 50.2, I didn't leave off any sig figs.
Oh, okay. So you carried all the digits in your calculator?
I carried like 8 sig figs.
All right. So then, not eight digits because you aren't allowed that many sig figs. And so this turns out by dropping this. You know, you said this was an 8. So by dropping the 8 here, this made an impact on this. And so this is what we call a round-off error versus a mathematical error. And so if everybody was getting 49.1, then I'd go check it and see, is that a round-off? And are you consistent with the rules? If so, then yeah. But if you're doing artificial round-offs that are too high, then I'll deduct. Okay.
So on the test, you want the fourth sig fig to be the one that gets cut off?
No, on the test it depends on what we're allowed, and so here, you know, because we only had 3 sig figs here, this is why I was expecting this to be much better. We're carrying 4 digits, and so we should have been able to get much closer. And so this morning when somebody got 50.19, I didn't think about it because that sounds normal, you know. This is round to 50.2, and so that just threw me off that this afternoon we're getting 49.1, and so I need to go back through, but it's going to take a little bit of time to figure out exactly why. But if that's the case, then I would just carry all the digits like you did and then see, well, it was just round-off error. It's just because we were dropping these digits. But was the round-off error allowed or was it not allowed? And the round-off error is going to be allowed here because, you know, really we're only allowed 3 sig figs, we're carrying 1 extra. By carrying 2 extra, we would get a closer answer, right? But if you did this, let's say, you know, you went from 0.0168 to just 0.017, then that's not allowed because you're doing the intermediate round off, and then it's going to throw it off, you know, either way,
So you
up or
round
down. You only round off at the end. Okay. And so this one turns out to be a round off, but, you know, round off usually isn't that big, but I guess for this particular problem it is. You know, especially since we were carrying 4 digits, which throws me off. But anyway, I just wanted to figure out why. And so somebody must have rounded on the quadratic when they punched in the numbers, and that's why I got a different X this morning.
Solution manuals steps, but it doesn't show those
You got to watch out for the solutions manual, because sometimes the solutions manual, the reason why I emphasize this thing about intermediate round off is because the solutions manual is notorious for rounding intermediate steps.
Yeah,
And it always leads to an error. For example, let's say you're supposed to earn 0.04 cents. Let's say 0.4 cents per day interest, right? 0.4 cents per day interest, and somebody just, okay, that's close enough to 0. They just round it to 0 every day, you know? Then after a year, you're going to end up with 0 earnings, right, when you should earn a lot more. So the same thing. Let's say you're supposed to earn 1.4 cents, but they rounded it to 1 cent per day. You know, after a year, the cumulative effect is going to be a lot of money. Initially, it's just 0.4 cents. And so the same thing happens with round off, and so this is why, you know, I worry about the solutions guide, because the solutions guide, it depends. There are 5 people who authored the solutions guide. And so it depends on who wrote the answer to that problem. And some of the people, they just, you know, it's not consistent. And so somebody needs to go back through and edit that. Plus, there are some errors in the solutions guide that you'll see later. And so watch out for the solutions guide sometimes. Okay. All right, we'll stop here and then.